Okay, at this time, you should have the enough knowledge to understand our new topic. Why? Because we went deeply into three-dimensional spaces, vectorial calculus, um, partial derivatives, and so far and so on. Now it's the time to combine all those topics learned into this new topic that we are going to cover today. Okay, this new topic is named directional derivatives, and gradient vector. Gradient vector, directional derivatives. This little sign here is the nabla operator. So we are going to talk a little bit about this nabla operator and what it means. And this is very closely related to the gradient vector. Okay, I'm sharing this picture. As you can see, surface, this blue surface is the result of the main equation that rules this relationship. In this case, let me change the color. So all the blue is some value of z that equals a function of x and y. All the blue surface. Okay. Then if you see uh, in the first time we were calculating the partial derivatives for x and y, holding either x or y constant to capture the change or or the rate of change of a variable x in z, holding y constant, or the effect in z of the variable y holding x constant. But the constraint on that scenario is that we are only uh, having, or we are only getting the rate of change, let's say for this surface, only in this direction. In this direction, you will have the derivative with respect to y. And if you calculate the partial derivatives in this direction, you will have the rate of change with respect to x. But sometimes it is not possible to do or to get tied only to these two directions. What if we need some other direction like this? This is, let's say, certain amount of x plus certain amount of y, because it's not only x and it is not only y. We have this line here that it goes from to a different direction than y and x, and we need to know how to calculate the derivative of this function, because sometimes we need to calculate this curve here or the tangent line to any point P that goes in this direction, not necessarily in y or x direction. And that's the reason why we need to know how to calculate the directional derivatives, because directional derivatives is not only those that goes from all the way the x-axis on the y-axis, something else like this, a certain amount of x plus a certain amount of y. In this case, we can say that this certain amount of x or certain amount of y is named the unit vector, or any directional vector that goes precisely in the direction that we want in order to calculate that rate of change or that derivative. Okay, so let's move on with this. Let me change the color again. Um, as a recap, the partial derivative of x and y, as we see here, represents the rate of change of the unit vectors I and j. If you remember, x, the x-axis in your vectorial is I hat, and the y-axis is equal to y. Okay, so this is a vectorial relation between these two, and when we calculate the normal partial derivatives, we are getting the rate of change in the direction of I or in the direction of j. So suppose that we need to find the rate of change of z at any x sub 0, y sub 0 in the direction of an arbitrary unit vector named u, in this case, this one. And if you remember from your previous lectures, if you have a vector u and we have this x-axis and this y-axis, you can have these points of reference so you can calculate the coordinates or the components of this vector. If this is the base, the yz x-axis, and you have these components here, you can have the direction of this vector with the vectorial components of it. So this new u vector is going to be defined by these components a and b, which is this is a and this is b. And the h is a scalar or a constant. So we need to have this constant times this a component, this constant times this b component, to have the direction and magnitude of this vector. And this vector is going to be the line that this tangent line is going to follow to get the derivative of this function, but not on the x or the y-axis, but in any direction. Okay. To do this, we consider the surface S, which is the blue surface that is shown here in the picture, with the equation z equals f x of y, which I already explained here. And let uh, z sub 0 equals f x sub 0 y sub 0 be a point in the surface. And let this point lie on the surface S. So in this case, we have this point P over here. This is point P, and this is somewhere in the surface of this function. So we have that point P. If we project a vertical line that passes through the point P in the direction of the vector u, and you can see that that vertical line that goes from P in the direction of U is intersecting the surface S in the curve C. And the slope of the tangent line T to C and P is the rate of change of Z in the direction of U. Okay, what does this mean? Well, it means that we have this point here, and the projection of this point P is the beginning or the start of this vector U, and we have the length of this, which is h from here to here, and this curve along the surface is intersecting with this plane all the surface S, and the tangent line, in this case this one, is a tangent line to the curve over the point P. Okay, so it is the same that you have done before with the y-axis and x-axis. The only difference is that now we are adding this directional component, and it has to be somehow a way to calculate the angle of or the direction and the magnitude of this vector, because this is what is going to give us the result of what we are looking for, which is the calculation of the rate of change. Okay, now if we have a point Q, which is another point on the curve C, and we have a new vector, which is the P prime Q prime, and this P prime Q prime are the projections of the points PQ on the top of the on the XY plane. Then the vector P prime Q prime is parallel to U, or to the unit vector U, and so the vector P prime Q prime is equal to H times U. Remember that H is a constant or an scalar, and this HU is the components HA, HB for some scalar H. Therefore, we can conclude that X minus X sub 0 is equal to H times A, and Y minus Y sub 0 is equal to H times B. And this is the formula that you have been working with a lot of times before this topic, because this is the rate of change between some point of reference on the x-axis, and this is the difference, or the delta, between 2 points in the y-axis, and these two differences are resulting in the components of the triangle that we are using to estimate or to calculate the unit vector that is going to be our direction for the derivative that we are interested in calculate. So the difference on z over h, which is in this case, the difference in z is the difference from here, in this case, to here. If we project a flat line all the way here, and we have this point here, this difference over here is the delta of z. And the delta of z is how the surface is changing when I'm moving across this vector. This is the P prime point, which is a projection from the P point. And this is the Q prime point, which is a projection of the first or the original Q point. So if I move from P prime to Q prime, this is a vector which is the same as the vector U. And if you see here, from this point P to this point Q, there are some change in the height of the level of Z, because this is a curve. And that change, I'm going to give that change to the displacement of this vector u all along the surface. Okay, let's see this in a more visual way. Let's switch to the GeoGebra application. This is an applet that is available for you there, and this is showing exactly that what we are covering in this topic. So we have this surface. This is a point on every on any area of the surface. This line is the tangent line, which represents the derivative of the function to this point on the surface. And the plane, this green or light green plane, is the plane that is formed by this line and is cutting a section all across this surface. Okay, so in this case, what we are getting here is the partial derivative with respect to this axis only. If we want to move the angle to see, let's move the angle to 90 degrees. And now we have the partial derivative of the function with respect to this axis. Okay, so what we have done in the past is just to calculate these two partial derivatives across the x-axis and across the y-axis. But now, with the directional derivative, we can set any arbitrary angle like this, and you can have the value for the derivative for a point in that specific area on the top of the surface. Okay, so we are not longer dealing with this or with this, and we can get the derivative of the function to a point with any direction thanks to the directional derivative. Okay, so I'm expecting this to be clear enough for you. And on our next video, let's work an exercise so we can have this a little bit more clear.